Welcome to SS2 Physics, Term 1, Week 6. The relationship between electricity and magnetism is one of the great discoveries of modern science. In 1820, Hans Christian Ørsted discovered that an electric current produces a magnetic field around it, connecting two phenomena that had previously been thought unrelated. This discovery led directly to the invention of electric motors, generators, transformers, and electromagnets, technologies that power our modern world. By the end of this lesson, you will describe the magnetic field around a current-carrying conductor, apply the right-hand rule, understand the motor effect and the force on a current-carrying conductor, and describe applications including the DC electric motor. Let us begin. When an electric current flows through a straight wire, it creates a circular magnetic field around the wire. The direction of this field is given by the right-hand grip rule. Point your right thumb in the direction of the conventional current, from positive to negative, and your cord fingers show the direction of the magnetic field lines. If you reverse the current, the field reverses. The strength of the magnetic field, magnetic flux density, B, increases with greater current and decreases with distance from the wire. For a long straight wire, B equals mu naught times I divided by 2 pi times R, where mu naught is the permeability of free space, I is the current, and R is the distance from the wire. A solenoid is a coil of wire that, when carrying current, produces a magnetic field similar to a bar magnet. The right-hand grip rule applied to the solenoid tells you which end is the north pole, the end where field lines emerge. Adding an iron core dramatically increases the magnetic field strength, creating an electromagnet. Electromagnets are used in cranes to lift scrap metal, in electric bells, in relays, and in hospital MRI machines. When a current-carrying conductor is placed in an external magnetic field, it experiences a force. This is called the motor effect, and it is the principle behind electric motors. The force F on the conductor is given by F equals B times I times L times sin theta, where B is the magnetic flux density in Teslas, I is the current in amperes, L is the length of the conductor in the field, and theta is the angle between the conductor and the magnetic field. Maximum force occurs when the conductor is perpendicular to the field, theta equals 90 degrees, so sin theta equals 1 F equals BIL. The direction of this force is found using Fleming's left-hand rule. Hold out your left hand with the thumb, index finger, and middle finger mutually perpendicular. The index finger points in the direction of the magnetic field, north to south, the middle finger points in the direction of the conventional current, and the thumb points in the direction of the force, motion. Example: a wire of length 0.3 m carries a current of 5 A in a magnetic field of flux density 0.40 perpendicular to the wire. Force equals BIL equals 0.4 times 5 times 0.3 equals 0.6 newtons. This principle drives the DC electric motor. Current-carrying coils in a magnetic field experience a turning force, torque, causing the motor to spin. The DC electric motor converts electrical energy into mechanical energy using the motor effect. Key components: armature coil, the rotating part, permanent magnet, provides external field, commutator, reverses current direction every half turn to maintain continuous rotation, and carbon brushes, maintain electrical contact with the rotating commutator. As the coil rotates, the commutator ensures current always flows in the correct direction to maintain the torque. Without the commutator, the coil would oscillate back and forth rather than spinning continuously. Practical applications of electromagnetic effects include electric bells, electromagnet attracts striker, relay switches, small current controls large current, circuit breakers, magnetic force strip switch when current is too high, loudspeakers, varying current in coil creates varying force, producing sound, and galvanometers, current detection using deflection of a coil. Summary: current creates a circular magnetic field, right-hand grip rule for direction. Force on conductor, F equals BIL sin theta. Direction of force, Fleming's left-hand rule. DC motor uses commutator to maintain continuous rotation. Electromagnets used in cranes, bells, relays, and medical equipment.